This is the third and final example problem that's found at the end of your heat and temperature reading packet. On this problem, we're going to look at the total amount of energy needed to convert a quantity of water into steam. Because the phases water and steam are used to describe H2O, that means we're going to need to draw a phase change graph to help us organize all of the numbers that are provided in this problem. Like all these problems, staying organized is key. So the first thing we're going to do is to ID the variables. Start by reading the problem. The first word is how. It's a question word, many calories. That means we're going to find delta H when we're solving for this. And it says the word heat there to also remind us that. Given this mass, 130 grams of water, and we have these two values that are provided to us in the problem. So the only variable that we really know right off the bat is the 130 grams. We don't know any other variables because there's a phase change that occurs here. Steam and water are two different phases, which means that we need to draw a graph to analyze our other variables. So start by drawing a graph. On that graph, place the two temperatures that are given to you, the 110 and then the 40. Again, these graphs don't have to be to scale, they're just to help us organize our thinking. The other thing we're going to think about then is there an important temperature for this substance, water, in between these two? And there is. That important temperature happens to be 100, which is the boiling point, condensing point of water. Once you have that point made, draw a plateau, a flat part of a graph at that temperature. Connect your low temperature to one end. Then on the other end of that plateau, go up to your high temperature. Label your graph 1, 2, 3, which means there's going to be 3 different math problems. Most of the problems that we have with a phase change graph are going to have odd numbers, either 3 or 5, so keep that in mind. Then for your sloped portions of your graph, for your diagonal portions, figure out your delta T's. Remember, during the diagonal portion, the temperature is changing. 100 minus 40 is 60. And then for phase 3 of our graph, delta T is 110 minus 100, which is 10 degrees C. For each of these, we also have a specific heat capacity of that substance. For liquid water at phase 1 of our graph, the value is 1. For section 3 of our graph, the number is 0.49, and that's because greater than 100 is going to be steam. Steam's specific heat capacity is 0.49 calories per gram degree C. At step 2, we're going to be looking at a heat of either fusion or vaporization, and you need to think about what's happening at this temperature. We're turning liquid water into a vapor, so vapors involved, which mean vaporization. So that number is 540, which is the number you need to memorize. Because we have 3 sections of our graph, we're going to do 3 math problems. So now we're into the second step of our problem solving, and that's to plug numbers in. Because this problem only gives us one mass value, we're going to use delta H equals MC delta T for most of these. All of these are going to be changing heat. All of these are going to use the mass. And we know that because heat is an extensive property. Extensive properties are based on the size of the sample. For 1 and 3, we have to multiply by C, which is our specific heat capacity. For phase 1, the value is 1. For phase 3 of our graph, it is 0.49. And I wrote those down to help myself stay organized. Finally, for 1 and 3, there's a change in temperature, which means we have to use our delta T value that we already figured out. For part 1 of our graph, it's 60. For part 2 of our graph, it's 10. Or excuse me, for part 3 of our graph, it's 10. For part 2 of our graph, we need to multiply by the heat of vaporization value, which is 540 calories per gram of that substance. Because this is a flat part of our graph, there's no way we can do a delta T, which is why we don't have delta T involved in section 2 of our graph. Then you're just going to multiply these numbers to get an initial value for each part of your graph. For part 1, the change in heat is 7,800 calories, little c calories. For part 2, the change in heat is 70,200 calories. These would come from your calculator. And number 3, the change in heat is 637 little c calories. Notice I omitted using the labels, but if you were to use the labels in all cases, all units besides calories would cross off, which would make sense since we're solving for delta H, which is measuring calories. For each of these sections of the problem, you need to determine your sig figs. The 130.0 has 4 sig figs. The specific heats won't count. The 60 is going to have 3 sig figs because we're taking 100 minus 40.0. So that 0.0 is our third sig fig, so 3 sig figs in our answer. Number 2 would have 4 sig figs because the 130 has 4. And we're not going to use these known values like 540, 1, or 6, or 100 in our subtraction as sig fig important numbers. They are not measurements, they're known values that are constants. In part 3 of our problem, we have 3 sig figs, and again that's coming from the 10.0, which would put us to right here at the 1's place value. Why do I care about those place values? It's because we're going to sum these together, and the rule for addition and subtraction is to look at place values. The first number goes out to the 10s, the second goes to the 10s, the third one goes to the 1s. 10s is the further left place value, which is how you determine sig figs using addition and subtraction rules. If you sum these numbers in your calculator, you initially get 78,637. We need to round to the 10s position, giving us 78,640. So the 4 stays in the 10s. We can put a 0 here as long as we don't do a decimal point. That doesn't change the sig figs. And then that's in the little c calories. Box your answer so you can find it.